So, you've probably heard that quantum computers are going to solve some of the world's biggest problems. But there's always been this huge catch. The quantum information itself is just incredibly fragile. I mean, the real challenge is how do you protect something that can be destroyed by just looking at it the wrong way? Well, today we're diving into what might be the next great leap in solving that problem: dynamic surface codes.
Okay, so here's our game plan. First, we'll get right into the weeds of the quantum noise problem. Then, we'll look at the first big solution, these things called static codes, and why they kinda hit a wall. After that, we'll meet the hero of our story, dynamic circuits. We're going to break down 3 really cool, powerful new solutions, and then we'll tie it all together to see how this puts us on the path to truly fault-tolerant quantum computing.
All right, let's just start with that core challenge. You see, the very thing that makes quantum computers so incredibly powerful, their insane sensitivity, is also their greatest weakness. It's what makes them so unstable.
I love this metaphor. Picture this. You're trying to write a really complex message on the surface of a soap bubble, right? The slightest little breeze, a tiny vibration, and poof, your message is just gone. That is exactly the problem that quantum researchers are up against. The individual quantum bits, the qubits, they're just like those soap bubbles, constantly getting wiped out by any little bit of noise from the environment.
So what's the solution? It's a brilliantly simple idea called quantum error correction, or QEC. Instead of relying on just one of those fragile soap bubble physical qubits, you bundle a whole bunch of them together, and that collective creates a single, super robust, error-corrected logical qubit. It's like we're building a digital safe, that's our logical qubit, to protect the fragile message inside.
Now, the first huge breakthrough in building this quantum safe was something called the static surface code. And listen, it was a massive milestone. It proved error correction wasn't just a fantasy, but as we're about to see, that shield it created was, well, a little too rigid.
So what do we even mean by static here? It basically means the quantum computer runs one single unchanging set of instructions over and over and over again. It's a fixed routine, and its only job is to constantly check for errors and fix them. Think of it like a security guard on patrol who walks the exact same route every single hour, no matter what. The circuit checks for errors, fixes them, and then boom, right back to the start of the same cycle. And you know, that repetition does provide stability. It was the key to proving that QEC could even work in the first place. But that rigid, repeating pattern, it has some pretty serious drawbacks. Like, what if one of your physical qubits just dies, a dropout? A static code has a really hard time working around that. It also kind of locks you into very specific hardware designs, and it's vulnerable to these really sneaky errors, like something called leakage, where a qubit just jumps out of its assigned energy state. So yeah, that fixed shield, it's got some cracks.
And this is where things get really exciting. To get past the limits of that rigid defense, researchers developed a much smarter, much more adaptable shield, the dynamic circuit.
Okay, check this out, because this visual really nails the core difference. With the static code on the left, the regions that detect errors are like tiles on a floor, a perfect repeating square pattern, always the same. But look at the dynamic code on the right. The pattern of those detecting regions actually changes and alternates with every single cycle. Our guard isn't walking the same route anymore. They're changing it up, which lets them spot problems they would have missed before.
And look, this new flexible approach isn't just some cool idea on a whiteboard. Researchers have already built and tested dynamic circuits that solve very specific, very real problems. Let's take a look at 3 of them right now. First up, we've got the hexagonal circuit. Now, one of the biggest headaches in building quantum computers is just the physical wiring. Static codes demand really complex connections. This dynamic solution tackles that problem head-on, making the hardware itself way more efficient and, frankly, easier to build. And this chart just lays it out perfectly. A standard static code, that square lattice, needs each qubit to be connected to 4 of its neighbors, 4 couplers. But by using this dynamic hexagonal circuit, you only need 3. And that might not sound like a huge deal, but dropping from 4 to 3 connections per qubit is a massive simplification in chip design, which can lead to much better performance overall.
All right, solution number 2 is the walking circuit. And this one is designed to fight that sneaky leakage error we were just talking about, where qubits decide to just pop out of their computational states and start causing all sorts of problems.
So the trick here is pretty clever. The circuit periodically swaps the roles of the data qubits and the measure qubits that check them. By doing this, it makes sure every qubit gets reset over time. And the result? It's huge. those nasty, lingering correlated errors get smacked down by over an order of magnitude. That is a massive, massive improvement.
And for our third trick, we have the iSWAP circuit. Now this one's a real game changer because it proves you're not stuck using just one kind of quantum gate for error correction. This circuit successfully uses a totally different tool from the toolbox, the iSWAP gate, to get the job done.
And guess what? It totally works. It achieved an error suppression factor of 1.56. Now the key takeaway here isn't just the number, it's that this proves it's possible. It opens the door for engineers to design future quantum chips that are optimized for different, maybe even better kinds of gates. The toolkit just got a whole lot bigger.
Okay, so we've seen these three really cool, specific solutions. But let's zoom out. What's the big picture here? What does this new dynamic toolkit really mean for the future? Well, it's all about paving the road to the ultimate goal, a truly fault-tolerant quantum computer.
You know, there's a line from the research paper that just nails it. It says, dynamic circuits open new avenues for co-designing quantum hardware and error correction protocols. For the first time, the people building the chips and the people writing the error correction software can actually work together, in harmony, instead of being locked into one rigid way of doing things. So let's just recap the huge advantages we've unlocked here. We get way more flexibility in how we design the hardware, we get a bigger menu of quantum gates to choose from, and maybe most importantly, we get the ability to dynamically work around those inevitable broken qubits. All of this is pushing us so much closer to that next holy grail, creating a logical qubit that can finally live long enough to do something truly world-changing.
Look, this shift, going from a rigid, static shield to a smart, adaptable, dynamic defense system, it's a profound step forward. It makes the whole idea of building a quantum computer more robust, more flexible, and honestly, just more practical. And that leaves us with the ultimate question. With these smarter defenses getting better and better at protecting quantum information, what are the problems we're finally going to unlock? What challenges in medicine, or new materials, or fundamental science are we about to solve?
You know, we hear all the time that AI is this global revolution, but what if that revolution only speaks two languages? Today, we're diving into the story of a project called Solar Open, and how it's trying to tackle one of AI's biggest challenges, to build a future where this tech is truly for everyone.
And that really is the central question, isn't it? Because right now, the answer isn't a simple yes. We think of AI as this world-changing technology, but we have to step back and ask, is it actually serving the whole world?
And here's the reality check. The scales are tipped, and they're tipped heavily. The most powerful, most advanced AI models out there are overwhelmingly fluent in just English and Chinese. This isn't some small bias, it's a massive structural imbalance that could leave most of the world on the sidelines.
And this gets us right to the heart of it, what we can call AI's big language problem. It's a fundamental challenge that really questions the promise of this technology.
Because when AI only speaks a couple of languages really well, it creates a whole new kind of digital divide. It's pushing entire communities, cultures, and their economies to the wrong side of this technological frontier, all because their language just wasn't a priority. So, to make this feel a bit more real, let's zoom in on a specific case. A team at Upstage decided to tackle this problem head-on, and they focused on the Korean language, which is a perfect example of a language that's digitally vibrant but totally underserved by AI.
And here's exactly why it's such a tough nut to crack. Get this, even though 80 million people speak Korean, it makes up just a tiny fraction, 0.8%, of all the content on the indexed web. Just for comparison, English is over 50%. When you're training an AI, data is literally the food it eats. So what do you do when the pantry's almost empty? And it's not just about how much data you have, it's about how the AI actually reads it. And that's where something called a tokenizer comes in. Think of it like this. It's how an AI learns to see words. A tokenizer that was built for English is just going to stumble over Korean, breaking words into clunky, meaningless pieces. It's super inefficient. A good custom-built tokenizer, on the other hand, reads fluently because it actually understands the language's structure. Getting this right is absolutely critical.
So you're facing these massive hurdles, right? Not enough data, and the existing tools can't even read the language properly. Well, the team came up with a really brilliant three-part solution to fix it.
Here's the game plan, and it's so smart. First, if the data you need doesn't exist, just create it. Second, don't just dump all that data on the model at once. Teach it with a smart step-by-step curriculum. And third,
build the model efficiently, using an architecture that works kind of like a team of specialists.
Okay, let's talk about that first step, creating data. And we are not talking about a small amount here. The team synthetically generated 4.5 trillion tokens of high-quality data. To try and put that into perspective, that's thousands of times bigger than the entire English Wikipedia. It's like if you can't find the library you need, you just go out and build a bigger, better one from scratch.
Now, this curriculum part is just so clever. They didn't start with perfect, pristine data. No, they started with a huge, diverse, even noisy data set just to build a broad foundation of knowledge. Then, they progressively refined it, making the data cleaner and higher quality. And finally, they focused on only the absolute best, most culturally specific content. It's kind of like going from skimming the entire internet to intensely studying a curated set of encyclopedias. And that third step, the architecture, is just genius. SolarOpen uses a technique called mixture of experts, or MoE. Now, instead of one giant AI brain trying to be a generalist at everything, an MoE model is more like a team of specialists. When a question comes in, the system routes it to the right expert for that specific job. This makes everything so much more efficient, both for training and for performance.
So, after all this incredible work, making data from scratch, designing a smart curriculum, using a specialized architecture, what did they actually build?
Well, the result is SolarOpen. It's a huge 102 billion parameter model, which puts it right up there with some of the heavy hitters in the field. But here's the cool part. Because of that mixture of experts design, it only uses about 12 billion of those parameters for any single task, making it incredibly fast and efficient. And most importantly, it was built from the ground up to be a true bilingual in both Korean and English.
All right, let's see the proof. Remember that custom tokenizer we talked about? Well, look at this. You can see right here that for Korean text, it is way more efficient than the tokenizers used in those big global models. This means it can literally read Korean faster and way more intelligently.
And this isn't just some advantage in a lab. Nope. This efficiency holds up in the real world, in actual conversations. On real chat data, SolarOpen's tokenizer keeps its lead, which translates to faster, smarter responses, and a much deeper understanding of what a user is actually trying to say. Okay, being efficient is one thing, but is it actually smarter? Well, this chart here shows a direct head-to-head competition on a test of Korean general knowledge. You can see SolarOpen's score on the left, almost at 80, just blowing past a comparable global model. It doesn't just read Korean better, it flat out understands Korean better.
And this is where the story gets really, really exciting. Because the success of SolarOpen isn't just a win for one language. It's pointing towards something much, much bigger. A blueprint for a truly global AI.
The real key takeaway here is that the methodology is the true innovation. The model is amazing, sure, but the process, generating data, using a smart curriculum, and leveraging these efficient architectures, that's a strategy you can repeat. This is a blueprint for democratizing AI and bringing it to any language. The researchers behind the whole project really said it best. The approach applies to any language lacking sufficient training data and frontier quality models. This wasn't some one-off trick. It's a foundational strategy for any language that's been left behind by the AI boom.
And that leaves us with one final, very exciting question. We've seen the proof, we have the blueprint. So which language is going to be next? The possibilities, for the first time, are wide open.
You know, imagine an AI that can just dive into incredibly complex software, sniff out the bugs, and then fix them all on its own. It's one of the biggest promises in tech right now. But what if we could take it a step further? What if that AI could learn from the collective wisdom of every human programmer who came before it? Well, that's exactly the idea we're going to unpack today.
So here's the thing. Today's AI coding agents, they're really powerful, no doubt. But when you throw them at messy, complex, real-world problems, they fail a lot. And the reason is actually pretty simple. They're basically operating in a closed world. They try to solve every single new bug completely from scratch, totally ignoring this massive history of problems that humans have already figured out.
Think about it like this. Imagine a brilliant detective, right? They've got all the latest and greatest forensic tools, but they've never studied a single past case. They have no experience to draw from. And that lack of wisdom, that's the fundamental problem we're talking about with these AI agents. I mean, GitHub is an absolute goldmine of knowledge with millions upon millions of solved bugs. But for an AI, it's just a chaotic mess.
The data is all unstructured, it's full of chatter, different coding styles, missing info. It's just noisy. There's been no good way for an AI to actually learn from this huge vault of human experience. Until now, that is. And this is where a brand new framework called MemGovern enters the picture. So if the AI agent is our brilliant but inexperienced detective, you can think of MemGovern as the master librarian, the one who builds a perfectly organized library of every single case ever solved. MemGovern's whole mission is to take that chaotic, messy history of human bug fixes on GitHub and just transform it. It carefully curates and standardizes all that data, creating this pristine, searchable library of experience that an AI can finally understand and, more importantly, learn from. So how in the world does MemGovern pull off this magic trick, turning all that chaos into perfect clarity? Well, it all comes down to a really clever pipeline it uses to build its library of experience. It's a super rigorous 3-stage process. First, it sifts through everything on GitHub to pick out only high-quality projects with complete bug fix records. Then it standardizes all that data, cleaning it up and reorganizing everything into one single consistent format. And finally, it actually uses another AI for quality control to verify every single entry and make sure that library is absolutely rock solid. And this is what you get at the end, a perfectly structured experience card. Now, what's so brilliant about this is the design. It cleanly separates the problem, which you see up top in the index layer with all the searchable symptoms, from the solution, which is down below in the resolution layer with the actual logic of the fix. This clean break is absolutely crucial for the AI to learn effectively. Okay, so MemGovern has built this incredible library. We're talking 135,000 of these pristine experience cards. The next huge question is, obviously, how does the AI agent actually use this library when it faces a brand new problem? It uses something way more sophisticated than just a simple keyword search. It's called agentic experience search. And it's basically a smart, multi-step process that's designed to mimic how an expert human developer would actually research a problem. It lets the agent not just find stuff, but explore and reason about past fixes. The agent really has 2 main tools at its disposal. First, it uses searching to quickly scan the top layer of millions of these cards, just like our detectives scanning the summaries of old case files. Then, once it finds a few promising leads, it uses browsing to dive deep into all the details of one single card to really understand the root cause and the strategy behind the fix. Okay, the whole theory sounds fantastic, right? A curated library of human knowledge and a smart AI to search it. But this is science, so we have to ask the big question. Does any of this actually work in the real world? Let's just put it plainly. Does giving an AI a library full of human experience actually make it a better coder? Does it really solve more bugs? And the answer is a big, resounding yes. On the incredibly difficult SWE-bench benchmark, MemGovern gave these AIs an average performance boost of 4.65%. Now, I know what you might be thinking, 4.65%? But in the world of AI performance benchmarks, that is a massive leap forward. And this chart really shows it wasn't just a fluke. Just look at that consistent improvement across a whole range of different AI models. It doesn't matter if it's a top-tier model like GPT-4 or a smaller one, MemGovern provides a significant boost to all of them. It effectively raises the IQ of any coding agent you pair it with. And let's look at a really concrete example, because this makes it so clear. On the left, you've got the AI agent without experience. It makes a really clumsy fix. Yeah, it stops the program from crashing, but it breaks the software's internal rules to do it. But on the right, the agent with MemGovern's guidance, it understands the deeper context from a past case and implements this elegant, correct, and truly human-like solution. The researchers themselves really summarized it perfectly. The standard AI applies a defensive bypass. You can think of that as just a quick patch. But the MemGovern-powered agent, it uses historical logic to create a semantically correct fix. It's literally the difference between slapping a bandage on a symptom and actually curing the disease. And when you kind of zoom out and think about it, you start to realize that this breakthrough is about so much more than just helping AIs fix software bugs. The whole method that MemGovern uses of systematically taming this messy, unstructured human data into a clean, agent-friendly library, that's a blueprint. You could use this exact same approach to teach AI from our collective knowledge in other super complex fields. Think law or medicine or scientific research. This work really opens up a fascinating new frontier. It's not just about building AI that can reason from scratch. It's about creating AI that can truly stand on the shoulders of giants by learning from all of our shared human history. Which, of course, leaves us with one last, really tantalizing question. What becomes possible then? All right, let's talk about the AI economy. We're going to cut through all the noise, all the hype, and get straight to the real data, thanks to a pretty groundbreaking new report. So, you know the big question, right? The one everyone's asking. Is AI this incredible productivity miracle, or is it a job killer? I mean, it feels like you hear both sides of that argument literally every single day. Well, guess what? We finally have some hard numbers to look at. The AI company Anthropic just dropped this huge report based on how real people are actually using their AI models. So yeah, let's dive right in and see what they uncovered. Okay, so to really get a handle on the impact here, the report gives us a totally new way of looking at this, a new lens, if you will, for how we interact with AI. They call them economic primitives. Now that sounds a little technical, but just think of them as the basic building blocks for understanding what AI is really doing. We're not just asking, are people using AI? No. We're looking way deeper. We're looking at things like, how complex is the task? What's the skill level of the person using it? How much freedom is the AI given? And this is the big one, how often does it actually succeed? All right, so with these new tools, these primitives, we can start answering some of the big questions. First up, who's actually using this stuff right now? And trust me, the answer is, well, it's pretty revealing. Okay, take a look at this. The thing that jumps out immediately is just how concentrated everything is. You'd think AI would be used everywhere for everything, right? But nope, it's still super skewed. A whopping 34% of all tasks are in computer and mathematical fields. We're talking coding, software development, that kind of thing. So it's a really powerful tool, for sure, but right now it's living in a pretty specific corner of the economy. And this concentration leads to a fascinating tale of two trends. See, on the global stage, adoption is pretty slow, and it's really tied to how wealthy a country is. But here in the US, it is a completely different story. AI is spreading like wildfire, about 10 times faster than major technologies from the last century. So you've got this super fast adoption, but it's definitely not happening everywhere at the same speed. Okay, so we know who's using it. But the next logical question is, how well is it actually performing? And this, my friends, is where we find a really surprising and important trade-off. First up, the really good news, especially if you're excited about productivity. The data shows that AI gives the biggest speed boosts on the hard stuff, the more complex, higher skill work. Get this. For tasks that need a college-level education, people saw a staggering 12x speed up. A 12 times speed up. I mean, this is exactly where that whole productivity miracle idea comes from. But, and this is a big but, here's the catch. On those exact same complex tasks where AI is so incredibly fast, it's also, well, less reliable. The success rate actually drops. It goes from 70% on simpler stuff down to 66% on the hard stuff. So yeah, it's way faster, but it also messes up more often when the work really matters. The report has a great name for this, the task horizon. And the takeaway is super important. It basically means there's a limit, a horizon, to what AI can reliably do right now. The bigger and more complex the job, the more likely it is to just fall short of that horizon. Okay, so that's the big picture, but let's bring it right down to you and me. What does all this data actually mean for your job? Is AI here to just remove tasks, or is it more about changing them? To figure that out, the report uses another cool metric. It's called effective AI coverage. Now, this isn't just about what tasks AI can try to do. This is way smarter. It measures the chunk of a job that AI can do successfully, and it even considers how important each of those tasks are. It's a much more realistic way to see the actual impact. And when you use that metric, you see two totally different paths emerge. Path 1, de-skilling. Think of a travel agent. Maybe AI takes over the really complex planning, a high-skill task. That leaves the human agent with the more routine stuff, like collecting payments. Path 2 is upskilling. Think of a real estate manager. Here, AI might automate all the boring admin work, the low-skill stuff, which frees up the manager to focus on high-skill work, like negotiating big contracts. So the million-dollar question is, which one is happening more? And the report's answer here is kind of startling. Right now, the net effect across the entire economy is actually de-skilling. Why? Because AI is pretty good at the kind of tasks that usually require higher education. So for now, it's taking on more of our high-skill work than our low-skill work. Okay, let's zoom back out again. We've got de-skilling, we've got these task horizons, we've got uneven adoption. With all that complexity, what's the real bottom-line impact on the economy? Well, the first number you see is huge. Just based on those speed-ups we saw earlier, AI could boost annual labor productivity growth by 1.8%. Now, to put that in perspective for you, that would be like going back to the economic boom years of the late 90s. It's a massive number. But you know where this is going, right? We already know that's not the full story. That incredible 1.8% number, it doesn't account for that task horizon we talked about. It doesn't account for all the times the AI fails and a person has to jump in to fix things or just start all over. So, once you adjust for how often AI actually succeeds in the real world, the number comes down to a more realistic 1%. Now, don't get me wrong, a 1% boost is still a massive, game-changing deal for the economy, but the drop from 1.8 shows you just how critical that reliability factor really is. And really, this brings us to the core conclusion of the whole report. And it's summed up perfectly by this quote. The big idea is this: just giving everyone access to AI isn't going to cut it. That's not enough. The real challenge, the essential part, is for us humans to develop the skills to use these powerful new tools in the right way. So maybe in the end, we've all been asking the wrong question. It's not really about how fast the AI is. The really crucial question, the one that's going to define our future, is how good can we get at learning how to use it?